So welcome back guys. Now let us discuss paging in action. So this is the moment which we have been waiting for. In this lecture video we will going to discuss an end-to-end example which demonstrate the concept of paging. So in our example, consider the following configuration of the system. The size of the virtual address space of the process, let us suppose it is 16 bytes, right? It means that in virtual address space of a process, there can be 16 virtual addresses. And to represent 16 virtual addresses, you need 4 bits. It means that the size of virtual address that is generated by CPU during the course of execution of a program is of 4 bits in size. Next, let us assume that the size of virtual page is 4 bytes. Now, since the size of a virtual page is 4 bytes, the virtual address space of a process will be fragmented into 4 virtual pages. Why 4 virtual pages? Because 16 divided by 4, where 16 is the size of process virtual address space and 4 is the size of a virtual page. It means that virtual address space of the process will be fragmented into 4 virtual pages. Now let us assume that the size of the main memory is 32 bytes. So diagram on the right hand side represents the main memory. Now since the virtual page size is equal to frame size, therefore the main memory will be fragmented into 8 frames. Why 8 frames? The size of the main memory divided by the size of the frame, which is 8. So the main memory will be fragmented into 8 frames. Now going forward, since the virtual address space of the process is fragmented into 4 virtual pages, it means that number of bits required to represent a virtual page uniquely is 2, right? Because 2 raised to the power 2 will give you 4. And finally, number of bits required to represent an address within a virtual page uniquely is 2 bits. Why 2 bits? Because the size of the virtual page is 4 bytes. It means that in one virtual page there will going to be 4 bytes and every byte has an address. Therefore you need 2 bytes to uniquely identify a byte within a virtual page. So I hope you understand all these calculations and assumptions. Now with this configuration of the system in place, now let us demonstrate how does paging works. Now let us suppose that your program is executing. Now during the course of execution of a program, we already know that CPU generates virtual addresses to perform read and write operation in physical memory. So let us suppose that, for example, CPU generates the virtual address 9, right? Now the binary representation of virtual address 9 is 1001, right? Now you can see that the binary representation of the virtual address has been split up into 2 parts. And each part comprises of 2 bits, right? Why 2 bits? Because number of bits required to represent a virtual page uniquely is 2 bits. And number of bits required to represent an address within a virtual page uniquely is again 2 bits. Therefore, virtual address that is generated by the CPU is decomposed into 2 parts and each part is 2 bits long. Now let us suppose that for the process in execution, the following is the page table. So you can see that a process has 4 virtual pages, page number 0, page number 1 and 2 and 3. Corresponding to this virtual page, you have a physical page, right? And each of these physical page is loaded into corresponding frame number in the main memory. So you can see, for example, that the physical page 1 is loaded in frame number 5, that is in this frame, right? Similarly, physical page number 2 is loaded in frame number 1, that is in this frame, right? Now we already know that the virtual address has been splitted up or decomposed into 2 parts. The first part is actually used to uniquely identify the virtual page number in the process virtual address space. So the decimal equivalent of the first part is 2, right? So it maps to the second virtual page in the process virtual table. Now virtual page number 2 has a mapping with physical page number 2 as per the page table. And we know that as per the page table, physical page number 2 is loaded in frame number 1, right? So the output of looking up into this page table using 2 as a key is frame number 1. So this is the output of looking up into the page table using the first 2 bits of the virtual address as a key into the page table. So till now we have located the frame number 1 in the main memory. Now the question is that which byte number within this frame we are trying to access. So now here starts the role of the second decomposed part of a virtual address. Now the decimal equivalent of the second decomposed part is 1. And we know that the second part of the virtual address is nothing but it is an offset within a virtual page. So it means that in a frame F1, starting with the first byte add an offset, you will end up with the physical address 5 of main memory. So please note that these numbers which are written on the left hand side of the physical memory are actually physical addresses which identify a location of a byte in a physical memory. So you can see that after adding the offset value to the starting address of frame F1, we end up getting the physical address 5. So it simply means that logical address 9, that is this address, maps to a physical address 5 in physical memory. So once the virtual address is successfully mapped to a corresponding physical address in the main memory, CPU then performs the read or write operation as per the instruction add physical address 5. So you can see that the concept of paging is very simple and easy to understand. So let me summarize what we have done so far. In the first step, CPU generates the virtual address and decomposes the virtual address into 2 parts, right? Using first part of the virtual address, locate the frame number of physical memory into which the physical page is loaded. Using second part of the virtual address, determine the offset value, right? And then add this offset value to the starting address of the frame which was determined in step number 2. So you can see that the paging process involves these following 4 steps. And the end result of the paging is that the virtual address that is generated by the CPU has been successfully mapped to some physical address of random access memory. And we already know that it is RAM or physical memory which actually stores the data. So it means that from the process perspective, the process performs read and write operation on the virtual address 9, right? Process always believes that it has 16 bytes of memory available to it and to be used. Why 16 bytes? Because from process perspective, the size of the virtual address space of the process is 16 bytes. Process is not even aware that there exists something called physical memory and physical addresses. It is the paging that is playing its role and successfully map the virtual address that is generated by the process to some physical address on physical memory. From the process perspective, process always believes that it is performing read and write operation on some address 9. But in reality, the read and write operation is being performed on physical address 5 on physical memory. So you can see that paging actually creates an illusion for a process. So if the process, for example, invokes the operation strncpy, pass 9 here and pass hell here followed by 4, which is the length of the string, it means that this string hell will be written in the physical memory in this way, HELL, right? because the virtual address 9 maps to the physical address 5 in the main memory, and starting from this address we are actually writing 4 byte of string, which is HELL. So you can see that in the physical memory, hell will be written in this manner. We already know that each character occupies 1 byte. So guys, going forward, if CPU generates the logical address 6, then this logical address 6 will map to the physical address 22 in main memory. Similarly, logical address 13 will map to the physical address 9, logical address 15 will map to the physical address 11, and logical address 3 will map to the physical address 15 in main memory. Now you already know the steps, how paging works, therefore I request you to actually verify whether these results are correct or not.